Okay, so our course name is R24 Manufacturing Process. So today's topic is forming and shaping of plastics and composite materials. Right. So in that we are going to discuss forming and shaping of plastics alone. Right. So today we are going to discuss only plastics. So these are the content we are going to see. The first one, introduction. Right. So introduction means how the plastics are evolved. Right. So the processing of plastic and the elastomers involves operations similar to those used in the forming and shaping of metals. So there is no different manufacturing process. Some customized machine is enough, right? So the process similar process for metal. The process for metal is processing of metal is similar to processing of plastics, right? So both are same working principles. The process of rubbers and elastomers began in the 1800, right? So in 18th century itself, it started. So discovery of vulcanization by C. Goodyear in 1839, and plastic began to develop in 1920, right? So 1920 itself they invented plastics. In 1940, designed and manufacturing of various processing equipment to make numerous consumer and industrial products in large quantity. Right, so first 1920 it's manufactured and 1940 the product are fabricated. 1917 reinforced plastics began to introduce, right? So and then in 2000 the rapid progress in the use of composite materials, right? So composite materials different from alloy. We will discuss in next class, right? So in 2000 rapid progress of use of composite materials with the unique properties and attendant challenges in producing them. Right, so these are some of the examples for plastics as well as elastomers. Right, so we are going to see this process, right? So for example, extrusion, injection molding, blow molding, rotational molding, thermoforming, compression molding, transfer molding, casting, and then processing of composite materials. So here the extrusions generally it uses a solid, continuous, uniform, solid or hollow complex cross section, high production rates, relatively low tooling cost and wide tolerance. So the comparisons, right? So extrusion process we can make any types of cross section. It may be the solid or hollow, or it may be the complex shapes, and the production rate is high, but tooling cost is very less. These are some of the advantages for extrusion. Similarly, injection molding, complex shapes of various size, thin walls, very high production rates, costly tooling, good diamonds like this. So the tooling part is a costly one. At the same time we can produce complex shapes. Blow molding, hollow or thin walled pots and bottles of various sizes, right? So if you want to make a bottles, you go with blow molding. Similarly, rotational molding, large hollow items, relatively simple shape, relatively low tooling cost, relatively low production rates. So blow molding generally used for water bottle, right? So the smaller one. If you want to fabricate water tank, right, assume that the tank is size, in terms of size it is a huge one. So the size, if the size increases, then you go with rotational molding, right? The thermoforming, shallow or relatively deep cavities, low tooling cost, medium production rate. So if you want a deep cavities product, you go with thermoforming. Tooling cost is low as well as production rate is also very medium, right? So compression molding, parts similar to impression die casting. So we already studied impression die casting. So the same product as like impression die casting, you go with transfer molding, right? So you go with compression molding, and the transfer molding more complex parts than compression molding, and then higher production rate, higher tooling cost, same scrap loss. So loss will be more. Similarly, the casting, it's a simple or intricate shapes made with rigid or flexible low cost models, low production rates. Processing and then the final one is to be processing of composite materials, long cycle times, expensive operation, low tooling cost depending on the process. These are some of the comparisons. So today we are going to see extrusion, injection molding, blow molding, rotational molding, thermoforming, compression molding, and transfer molding. So next class we are going to see casting as well as processing of composite materials. Right, so this is the type of material, right? What kind of material we are going to use, or that material, what should be the form. The form means whether it is in powder or it is a liquid or it's a pellet, right? So TP stands for thermoplastics, TS stands for thermosetting. So plastics can be classified as two way. One is a thermoplastic, thermosetting. So thermosetting means if you heated, then it will get the final set. So again you cannot reheat. It's a set. Thermoplastic means you can reheat. Right. So E stands for elastomers. Right. So both are category of plastics. Right. So the generally extrusion, injection molding, rotational molding, structural foam molding, compression molding, transfer molding, all needs all the process we can use for thermoplastics. Right. So thermosetting process can be used in injection molding as well as rotational, structural, compression molding. Right. So elastomers you can use extrusions, injection molding, and then compression molding. Right. So casting also you can use thermoplastic as well as thermosetting. Right. So if it is an extrusion process, if you want a sheet, you go with thermoforming. The main principle is extrusions. Right. So if you want a tube, or you go with blow molding or blown flame. So these are the categories. Right. So similarly, if it is a liquid material, right, so liquid or paste, thermosetting, you go with the reaction injection molding and fibers. If it is or you go with steel lithography. This is we already seen in one of the 3D printing process, right? So steel lithography. So these are the classifications of materials. Right. So first we are going to see the extrusion process. Right. So in extrusion, which produces the largest volume of plastics and the raw material in the form of thermoplastic pellets, granulars or powders are placed into the hooper and fed into the barrel of screw extruder. Right. So we can make a largest volume of plastics. Right. So with the help of extrusion, we can make a largest volume of plastics. The raw material in the form of thermoplastics pellets. Right. So the pellets, it may be the pellet or it may be the granular or it may be the powder, are placed in the hooper. The hooper is one we can store the raw material. Right. So hooper and fed into the barrel of screw extruder. So this is one of the screw extruder. So from this figure you can easily understand extrusion process. So here from bottom we have a motor and we have a gear reduction box. That gear it is used to reduce the speed of the screwdriver. Right. So screw extruder. Right. So and it is connected to the motor and we have a bearings. So bearings. So the raw material is injected in the hooper. The motor power is on, it will the metal is extruded, right? So the metal is extruded and we have a 3 section called feed section, melt section, melt and pumping section. So feed section generally used for input to provide the input material. Melt section where we increase the temperature of the raw material and it converts at the molten state, somewhat some melt state. And melt and pumping where we use we increase the pressure. Right. So finally we have a nozzle. Right. We have a nozzles and it will extrude. The barrel is equipped with the helical screw. So this is a barrel. The barrel is equipped with the helical screw. This is one of the helical screw that blends the pellets and conveys them down the barrel towards the die. So it is blend. It is blends the material. Right. So the pellet, the barrel heats and the internal frictions from the mechanical actions of the screw heat and the pellets are liquefies them. Right. So with the help of barrel heating as well as friction heat, the metal raw material is converted as the fused state. Right. The screw action also build up the pressure in the barrel. So at the same time pressure also increased. So screw have a 3 distinction section. One is a feed, melt, metering section. So feed section, melt and pumping, then we say it's a metering. So melt and pumping section we say it's a metering section. Right. So feed section conveys the material from the hooper into the central region of the barrel. So it is a passage. It acts as a passage. The input material it reaches via feed section to central part of barrel. Melt section also called as a compression or transition section, where the heat generated by the viscous shearing of the plastic pellets and by the external heaters causes the melting to begin. So where the heat will be increased with the help of friction as well as some external heater. We use some external heaters. The next one is a metering or pumping section, where additional shearing at a high rate we will create additional shearing and melting occur with pressure build up at the die. So the pressure will be die. So this is what the extrusion process. So applications are the plastic tubes and pipes are manufactured with the help of extrusion. Plastic coated electrical wire, polymer sheets and films, plastic films, polytetrafluoroethylene, right? So PTFE. In other way we say it's a Teflon. So these are the materials we can use and make a product by extrusion process, right? So the second process is injection molding. So it is similar to hot chamfer die casting, right? So we have a powder or pellets placed in the hooper, and it may be the piston or it may be the screw, reciprocating screw, right? So and we have a heating zones. So the metal is inserted, metal is poured in the hooper, it will pushed to nozzle via screw extruder or piston, and we have some heating zones, so it will increase the heat and it converts as the molten state. And we have a nozzle. That nozzle is connected to the mold. That mold we have a cavity. That cavity is nothing but our required shape. So the cavity is nothing but our required shape. So the metal is inserted, the ram is pushed. So and the pressure is increased. At the same time, heating zones will increase the heat. So the temperature converts the molten state and it is deposited in the die. Die has a cavity or opening. So based on our requirement, the cavity is formed. So after that, after curing, it will remove from the die. So this is the injection molding process. The pellets or granules are fed into the heated cylinder. So the pellets or granules are fed into the heated cylinder, and the melt is forced into the mold either by hydraulic plunger or by the rotating screw of an extruder. So there are two ways. One is ram or hydraulic ram or screw extruder, right? So as in plastic extrusion, the barrel is heated externally to promote melting of the polymer. So we add the heat to promote melting of the polymer. In injection molding machine, however, a far greater portion of heat transferred to the polymer is due to the frictional heating. So the friction also plays a major role. So some amount of heat will be generated with the help of frictional heating. So this is the sequence of operation in the injection molding of part with the reciprocating screw. Modern machines are of the screw type, right? So with the sequence of operation shown in figure, right? So first thing, build up polymer in front of screws buzzing. So first we store the raw material. So the extruder moves backwards, right? So extruder moves backwards because we add the metal. After this is generally used to identify the volume, how much metal we add inserted. After that, the enough amount of metal is added. The piston is moved forward. Forward direction. So this is a reverse direction. This is on a forward direction. So piston is moved forward direction. So the metal is forced. Metal is injected, right? So metal is injected into the cavity, right? So cavity which is present in the die. So the die is opened. After curing, the metal is removed. This is the sequence of injection molding. As the pressure build up at the mold entrance, the rotating screw begins to move backward because we add the metal under pressure to the predetermined distance. This movement controls the volume of material to be injected. The screw then stops the rotating and it's pushed forward hydraulically, forcing the molded plastic into the mold cavity at high pressure, right? So 7 to 200 megapascal. For thermoplastic, the molds are kept relatively cool at about 90 degrees Celsius, and thermoset pots are heated molds at about 200 degrees Celsius, where the polymerization and cross-linking takes place. So after the pot has cooled sufficiently or cured, the molds are open and the ejectors are used to remove the pot from the mold. So after injector and we let them allow to solidify or cure. So after that we will remove the material with the help of ejector pens. The molds are then closed and the process is repeated automatically. So this is what a injection molding. The applications are products includes cups, container, housings, tool handles, knobs, toys, plumbing fixtures, telephone receivers, electrical and communication equipment components. These are some of the applications for injection molding, right? So the next process is it's a blow molding. So this is similar to air blow in balloon, right? So air blow in balloon. So blow molding is a modified extrusion and the injection molding process. So this combines these two processes, modified extrusion and injection molding. So here extrusion means air as the extrusion act as the extrusion media, Injection molding means we have a die, right? So die and opening. So in extrusion blow molding, a tube or preform, right? So preform is first extruded. So first extruded, we have a extruder. The metal is extruded. It is a preform or rod, and it's then clamped into the mold. So after extrusion, the extruder material is clamped into the mold. The mold has a cavity, right? So and the knife will move and it will cut the extruder material. The close, so the blow pin is inserted from bottom, and the top of the portion is closed with the heating passages. So with the, and we have some key, the dies are heating with the help of heating passengers, and we inserted blow pin. The air is blown. The surface, internal surface of the cavity, the materials are sticking to the internal surface of the cavity. After that, after curing, it will remove and we will get the final step. This is a blow molding. This is a single step blow molding, right? So blow, depending on the material, the blow ratio may be the highest 7:1. It may be the 7:1. Blowing usually is done with the hot air blast at pressure ranging from 350 to 700 kilopascal. Drums with volume as large as 2000 liters can be made by this process. So typical die materials are steel, aluminium and beryllium coppers, right? So these are some of the materials we can use in blow molding. In some operation, the extrusion is continuous and the molds move with the tubing. The parts is then cooled and ejected from the mold. Corrugated plastic pipes and tubing are made by the continuous blow molding, in which the pipe or tubing is extruded horizontally and blown into moving molds. So these are some of the applications, right? So, and another one type of blow molding is we use parison. So parison mold. So injection blow molding, a short tubular piece called as a parison is injection molded into cool die. So first the extrusion part, right? So extrusion part, we have a parison mold and we place the material. We make a parison. So parison is nothing but on coat, right, and the raw material, right? So cool dies, and then it is transferred to the die. The same procedure are transferred to the die, and the pin is moved, right? So blow pin. So the air is blown. The parison is sticking to the internal surface of the cavity, right? Central surface of the cavity. After curing, we will remove the material. This is a blow molding. So here we use parisons. So parisons, right? That this is a single type. If you multiple or mass production, we go with indexing mechanisms, right? So simultaneously we will perform. So this is the stage 1. So this is a injection side. So the parison is injected and it is transferred to the second pin and blow pin. So here air is blown. The third stage is a stripper. So die opened and raw material, finished product is removed from the die. So we have a 3 stations. So the die is then opened and the parison transferred to the blow molding die by an indexing mechanisms, right? So the hot air is injected in the parison, expanding to its walls of the mold cavity. Typical products made are plastics, beverage bottles. Generally made by the polyethylene, polyether ketone, so peak and small hollow containers. So these are some of the products. A related process is stretch blow molding, in which the parison is expanded and elongated simultaneously, subjected to the polymer to biaxial stretching and thus enhancing its properties. So this is the blow molding process. Sometimes we use multilayer. So multilayer blow molding involves the use of co-extruded tubes, right, of parisons, and thus permits the production of multi-layer structure. So if you want a multi-layer, you need to use multi-layer blow molding, right? So a typical example of such product is plastic package for food, beverage, having such characteristics, odor and permeation barrier, taste and aroma production. So these are the records multiple coatings. So for example, if you want to pack vegetables, so in order to prevent release of odor, smell or other reasons, we need to coat multi-layer. So for this case, you can use multi-layer blow molding. So other application of this process are containers in the cosmetics, right? So cosmetic and the pharmaceutical industries. So these are some of the examples for blow molding. The next one is rotational molding. So most thermoplastics and some thermosets can be formed into large hollow, right? So hollow parts by rotational molding. In this process, a thin walled metal mold is made into 2 pieces. So here this is a metal mold. It is made by the two pieces, right? So two pieces, and is designed to rotate about two perpendicular axes. So this is a primary axis, another one is a secondary axis. So from this image you can easily observe that we have a inlet here, right? So pressurized fluid is insert here, and it will move on to the passage, and here the inlet. So right, so this is the inlet, and this one is the outlet. It is rotated about the x-axis as well as y-axis. So for these connections, so for each part cycle, a pre-measured quantity of powder plastic material. So we use powder plastic material is placed inside the warm mold. So the inside mold we place the powder, right? So the mold is to be the heated state. The powder is obtained from the polymerization process that precipitates the powder from a liquid. Then the mold is heated and it's rotated continuously about the two principal axes. So and then after placing the input material, raw material, the mold is heated and it is continuously rotated, right? So two primary axes. This action tumples the powder against the mold, where the heat fuses the powder without melting it. So for thermosetting parts, a chemical agent is added to the powder in order to improve the cross linking. Right, so the machines are highly automated when the parts moved by an indexing mechanism. So if you planning to use rotational molding for mass production, then you need to do some indexing mechanisms. Right, so applications are a large variety of parts are made by the rotational molding, such as storage tanks of various size, trays, cans, bold hulls, buckets, housings, large hollow toys, carrying cases, and footballs. So these are done by the rotational molding. Various metallic and plastic inserts or components also may be made integrally into the parts made by this process. In addition to powders, liquid polymers can be used in rotational molding. So that is called, we are going to see, that is called slush molding. So previous case we use raw material in the form of powder, but here we use raw material in the form of liquid, right? In addition to powder, liquid polymers can be used in rotational molding. The name called as a PVC plaster salts, right, being the most common material in this operation called slush molding or slush casting. The mold is heated and rotated simultaneously. The working principles are same, right? So we place the raw material and then it will heated and it will rotated. The same process only, but difference is here the raw material is in the liquid form. So due to the tumbling action, the polymer is forced against the inside walls of the mold, where it melts and coats the mold walls. The part is cooled while it is still rotating and removed by the opening of the mold. Right, the parts made are typically thin-walled products such as boots and toys. Right, so these are the rotational molding. The next process is transfer molding. So the name implies that transfer. Right, so thermoforming. So thermoforming is the process of forming thermoplastic sheets or films over a mold through the application of heat and pressure. Right, so this is generally uses heat and pressure. So the image you can easily observe that this various thermoforming process. The first one is straight vacuum forming. So here we place the plastic material and the top of the plastic sheet we insert the heater, and the bottom we have a pipe. From that pipe the air is sucked. So the plastics are deposited based on the shape. So this is a straight vacuum. The trap vacuum also similar this. And the force above sheet means instead of bottom shucking, here the top of the surface is shucked with the help of vacuum line. Right. So this is there is no air. Here we use some pressure. So ram is moved. So these are the various types of thermoforming process. In this process, a sheet is clamped and heated above the glass consistent temperature, usually by radiant heating, and forced against the mold surface through the application of a vacuum or air pressure. Right. So the sheets used in the thermoforming are available as coiled strip or as the length and width of the various size. They also are available filled with various materials for making parts with specific applications. So these are some of the application. The mold is generally at room temperature. Thus the shape produced becomes set upon contact with the mold. So generally we do room temperature. Because of low strength of material formed, the pressure difference caused by the vacuum usually is sufficient for forming. So we use only low strength material. That's why the pressure created by vacuum is enough to produce the final component. However, thicker and more complex parts require air pressure which may range from about 100 to 2000 kilopascal. So depending on the type of metal what we use. Mechanical means such as use of plugs also may be employed to help from the parts. So variation of the basic thermoforming process are shown in the figure 95. So this is the previous, right? So the mold for thermoforming usually are made of aluminium. So generally molds are produced made by the aluminium because of its high strength. Is not required because of its strength. Hence tooling is relatively inexpensive. So defects which may occur during a thermoforming are tearing of the sheet during forming, non-uniform wall thickness, improperly filled molds, poor part definition and lack of surface details. So these are the defects may occur during thermoforming. The next process is a compression molding. So in compression molding, a pre-shaped charge of material, pre-measured volume of powder or viscous mixture of liquid resins or filler material is placed directly into the heated mold cavity, and typically is around 200 degrees Celsius but can much higher. So this is similar to our forging process. So we place the object, we place the charge or we place the raw material between the mold, right, between the mold and the heating elements with the punches moved downwards, it will close the die. We have a three kind of shapes we can get. One is a positive type, right? So first one is the positive type, there is no extension, right? So exactly it matches. The second one is the flash type. So sorry, second one is the semi-positive, right? Semi-positive because it will stick onto the die as well as it will some part is ejected, right? So this is the third one is it is flash type, right? So the flash or the semi-positive, it need to be avoided. We need to do some secondary process to remove the process, right? So forming is done under pressure from the plug or from the upper half of the die. Thus the process somewhat similar to closed die forging of metals. So pressure ranges from about 10 to 150 megapascal, right? It may be the flash type or it may be the positive type or semi-positive type or flash types, right? These are the three categories. So sometimes we use secondary process, the flash. In order to remove the flash, we need to use a secondary process. The secondary process are, it may be the trimming or other process. Curing generally it take about 0.5 to 5 minutes, right? So only very less curing time depending on the material and part thickness and shape. If the thickness of the material, or final product of the thickness of the final product is to be high, then the curing takes more time. So applications are discs, handles, container caps, fittings, electrical and electronic components, washing machine, agitator and housings. These are some products we will make by compression molding. However, thermoplastics and elastomers are also produced by the compression molding, right? The next process is a transfer molding. So the name implies it transfer, right? So transfer molding represents the further development of compression molding. The uncured thermosetting resin is placed in the heated transfer pot or chamber, and after that metal is heated, it is injected into the heated closed molds. So the uncured thermosetting resin is placed on the die, and it will closed. If the temperature increases, it melt and it will occupy the space which is in die, right? So after that it will remove. After curing, the parts are removed. So depending on the type of machine used, ram, plunger or rotating screw feeder forces material through the narrow channels into the mold cavity at pressure up to 300 megapascal. So we can go with 300 megapascal. The viscous flow generates a considerable heat which raises the temperature of the material and homogenesis, right? So we can get the homogenesis mixture. And the curing takes place by the cross-linking. So the curings take place by the cross-linking. Applications are typical parts made by the transfer molding or electrical connectors and electronic components, rubber and silicone parts, and the encapsulation of microelectronic devices. So it is suitable particularly for intricate shapes, right? Complex shapes with very wall thicknesses, right? So up to this